Hi, we're back with another online presentation to help you understand the statistical part and data analysis for these courses. For this particular information, which will be about correlations between variables, the quiz that you're going to take at the end will include information from this presentation, the Doing Statistics in Excel presentation, and the one to follow this, Correlations Part 2, which demonstrates how the coefficient is calculated. So here we go. We want to look to see if there is some sort of relationship between how a group of individuals performs on multiple measures. So usually for these investigations, we are looking at a single set or sample of subjects, and we're going to look at more than one variable. And we want to look at the pattern of their responses, which means that the analysis that we're doing is going to look at the individual responses within the data set and analyze to see if the way the subjects respond on one variable has some kind of pattern, similarity, or likelihood that we can identify in the second variable. This helps us to identify whether or not the two variables are related. Now, we'll talk about the nature of the relationships later. We use a statistic called a correlation coefficient for this purpose. The correlation coefficient is a mathematical calculation that comes up with a number, which we'll explain shortly, that gives us an idea of the strength and the nature of that relationship. Here's another definition and explanation of this statistical tool. The correlation coefficient is usually, as I just said, calculated from the sample data measures, and we're looking at whether or not the pattern of a scatter plot between the two variables represents a linear or straight line relationship. And I'll come back to this in a little bit. We have a ton of different types of correlation coefficients, which again I'm going to explain shortly. We're going to work with the Pearson product moment correlation coefficient, or what's often called the Pearson correlation coefficient, because most of the variables you're collecting are either interval or ratio in nature, and these variables and these statistics therefore are appropriate to work together to make our analysis. When we calculate this coefficient, we use the small letter r to represent the correlation coefficient that's calculated for a sample. When we're talking about the entire population, they'll use the Greek letter rho. For our applications, we're going to use the letter r when we talk about correlation coefficients. As I mentioned a moment ago, there's multiple types of correlation coefficients. When both of your data sets, when both of your variables are interval or ratio in nature, we'll use the Pearson correlation coefficient. When both of the variables are ordinal in nature, we use the Spearman rank order correlation coefficient, which uses the data and evaluates the data from the standpoint that the numbers have no inherent numerical value. They simply indicate who's in what order. And the corrections in the calculations are done in the mathematical formula. The rest of the correlation types, phi, biserial, point biserial, and gamma, are used to compare either nominal to nominal, as we see with phi, nominal to a interval or ratio scale, which we call biserial, and this variable is usually dichotomous, as we see here, which means there are only two options. For example, on or off. Point biserial takes a dichotomous nominal and compares it to one scale of an interval or ratio, and then the gamma takes one nominal and one ordinal. For most of the data that we're using and for the variables that you've chosen to collect, we're going to use Pearson because your scales are interval or ratio in nature. So the Pearson correlation coefficient is calculated using this formula. Thank goodness you don't have to do that. I had to do it a number of times when I was doing my doctorate, and it's not a lot of fun. As you can see, there's a lot of times you have to sum up and you have to take squares and square roots and whatever. And as when we talked about standard deviations, we sometimes square things to get rid of negative values so that we don't have the problem of canceling out. When we just want to look at the magnitude of a number, we want to square it. And then we have to take a square root to get it back into the scale it was in originally. We're not going to have to do this by hand. The computer does this for you. All you have to do is figure out what the output is telling you. So we're going to look at the output. When you calculate a correlation coefficient, the statistical result will always be between -1 and 1. So mathematically we can say -1 is less than any value for r, and that is less than +1. That is always the case. If you calculate a correlation coefficient and you get a value that's outside of that range, there's something wrong with the calculation. So let's see how we interpret this. In a world where we could have no relationship between the two variables we're measuring, we would say that the correlation coefficient is equal to 0. Because of measurement error and other factors that get involved, we find out that rarely, if ever, will you see a correlation coefficient r equals 0 reported. When we look at -1, we see what's called a perfect negative correlation, which means that as one variable goes up, the other variable goes down. Or we can see a strong positive correlation, where as one variable goes up, the other variable goes up, and that would be a perfect linear relationship. The closer that the value of the number is to 0, the weaker the relationship between the two variables. Whether that relationship is direct or positive, or whether that relationship is inverse, or what we call negative. So here's what the graphs are going to look like. Notice that in this graph, everybody's in a nice straight line. Doesn't really happen in our real-life data sets because we've talked about introducing error. But this would give us a correlation coefficient of 1. This is a perfect positive correlation. As the x variable goes up, the y variable goes up, and there's a direct relationship. Notice that the closer we get to 0, the less that these graphs represent a straight line, and here there's no resemblance whatsoever. In this case, we're seeing negative correlations over here, where as one value becomes larger, the other value becomes smaller. So as x becomes larger, y becomes smaller. And that's the trend. Here's perfect, straight line. Here's not so perfect, pretty high, 0.8, 0.7. Here's not really good, 0.3, and here's data spread all over the place. Okay, so let's look at, again, put the numbers and the pictures together to just reinforce what we just talked about. And notice that the weaker the relationship gets, the less that the data points resemble a straight line. Okay, so here's some examples, again, of what plotting this data would look like for a variety of correlation coefficient values that would come from calculation. So here's a positive correlation of 0.4, 0.765. Notice that they're more grouped in a hot dog shape. Look how they really start to tighten up here. Okay, again, not quite so tight. 0.859, much more tight. 0.863, pretty tight. So as you look at the different pictures of the relationships, you can see what's going on here, and that the higher the R value, the tighter the dots are to the line, the stronger the relationship. Now let's look at some examples of what we're talking about here. Here's an example of something. In an ideal world, students should be able to relate to this. We have two things plotted on our graph here. The first of which is how much stuff you have to do. So like here, you got a lot of stuff you got to get done. And here, you got not so much you got to get done. And in the ideal world, if we plotted how much you procrastinate, in the ideal world, you can procrastinate all you want when you don't have much to do. And you don't procrastinate hardly at all when you got a lot to do. So that procrastination approximates an inverse relationship. In other words, the more I have to do, the less I procrastinate. The less I have to do, the more I procrastinate. And we would get a negative correlation coefficient showing us that relationship. But in reality, we all know that the more we have to do, the more we put it off. And the less we have to do, the less we tend to procrastinate. So here we have a direct relationship so that procrastination is related to and approximates how much stuff you have to do. This is a direct relationship. As one goes up, the other goes up. As one goes down, the other goes down. A real life example of what happens. Now, we know that figures don't lie. And one of the problems with correlation coefficients is that many people that use them don't know how to interpret them properly. So let's look at our picture here. We know that figures don't lie. So here's some facts about water that we can look at. For example, water can be chemically synthesized by burning rocket fuel. We know that. We know that overconsumption can cause you to sweat a lot or to pee a lot, or you might even die if you drink too much water. We know that 100% of all serial killers, rapists, and drug dealers have admitted to drinking water. Water is one of the primary ingredients in herbicides and pesticides and a lot of other toxic chemicals. Water is the leading cause of drowning, and 100% of all people exposed to water will die. Now, you could, if you wanted to, interpret a causation here, but you would be incorrect. We pretty much understand that, yes, people who die may have drank too much water. But just because these facts are true doesn't necessarily mean that there's a causation or that something happened which you should necessarily worry about. If you went by all of these facts and attempted to sit here and say, oh, well, look how bad this is, I should never drink water again, is that really a reasonable conclusion to come to? So we need to understand that when we do any analysis using a statistic, the way we interpret it is very important, and that we don't want to attempt to get more information than what the statistics and what the data tells us. A correlation coefficient is a useful tool, but it is not one from which you can imply that one thing caused another. Okay, so now let's look a little more deeply into this. We took a real data set, and this data was collected from 252 men. There were 16 variables, but for the purposes of our example, we're only going to look at 7. We're going to look at these 7 variables here, and all of these variables are circumferences around the particular body part that's being mentioned. Right? Now, for what we want to do, it would be real nice to use descriptives. Remember, we talked about means and standard deviations before. So when we want to get a picture of what these different variables might look like, or we want to talk about body fat in general, then we go to means and standard deviations, which give us a picture of what was the average for the group of 50 people that I told you we're going to analyze, and how did their values spread around that mean. The variables are quantitative and they are ratio, which means that 0 means 0. There's none of something. Well, that's good, because otherwise we got a problem. So for the sake of argument, we want to do a Pearson, so we want to see if there's some kind of relationship between somebody's body weight and their body fat. So we want to see if this variable is related to this variable. So we calculate the Pearson product moment correlation, or a Pearson R, for that purpose. And we run it in a computer and we put it in and we say, okay, here's what we get. As I told you before, and I looked at the formula, no place in the formula do you see means or averages or standard deviations. The correlation looks at response patterns of the individual subjects in the data we're looking at. So here's what we get. For the relationship between body fat and weight, we have a relationship of 0.595, which is a moderate to moderate, slightly strong. And we see here that's a positive relationship, and we're starting to see the points group in the general direction of a linear relationship. Not super tight, but we would call this moderate, and we would say that it gives us some information that would be of value. How do we calculate this? Well, that's where we're going next. In Correlations Part 2, we're going to look at how the Pearson correlation coefficient is calculated using Excel, which is something you will be able to do as part of your project. So your next task is to take a look at Correlations Part 2.